It imports the Google Drive module from the Google.Colab library. In the second line, the Google Drive is mounted to the Colab virtual machine VM and forced to be remounted if it is already mounted. Colab can access files and folders from the user's Google Drive using this code. As part of the code, the user must enter the folder name in their Google Drive where they have saved the unzipped assignment folder. If the folder name is empty, it raises an error. For the next step, the correct folder is accessed. Afterward, the code imports the sys module and adds the user's Google Drive path to the system path. Colab VM's Python interpreter is able to access and load Python files within the specified folder. Following that, the code downloads the CIFAR-10 dataset to the user's Google Drive if it doesn't already exist. It is commonly used in computer vision tasks, and the code downloads it to the specified location. Lastly, the code sets the current working directory to the specified folder in the Google Drive so it can access files in that folder and work with them within Colab. To begin, we import the necessary libraries such as NumPy and Matplotlib, as well as various custom functions from the CS231N package. In addition, it allows external modules to be loaded automatically and sets some default plot configurations. After defining rel error, we define a function. Using this function, you take two arrays, calculate their absolute difference, and then divide it by their maximum absolute value. The reason for this is to handle the case where one of the arrays or both arrays contain values that may result in a division by 0. This value is the relative error between the two arrays, which can be useful for comparing calculation accuracy. It's likely that the main purpose of this code is to set up and configure a convolutional neural network CNN for use with the CIFAR-10 dataset. In this dataset, there are 10 categories of images. As an example, the code may be used to train and test a CNN on subsets of the CIFAR-10 dataset for image classification. The solver class is responsible for optimizing the CNN training process, while the eval numerical gradient and eval numerical gradient array functions are used to evaluate gradient calculations. For tasks such as image classification, this code serves as a foundation for building and training a CNN on the CIFAR-10 dataset. It imports the necessary libraries, sets some default configurations, defines helpful functions, and imports custom code. Data is loaded from the CIFAR-10 data variable, which has already been pre-processed. There are various keys and values in the data variable, where each key represents a different aspect of the data, such as training images, training labels, test images, test labels, etc. Each key value pair in the data dictionary is iterated through using the for loop, and the key and the shape of the corresponding value are printed on each iteration. Since the values are arrays, the shape refers to their size and dimensions. It simply displays information about the data loaded, such as the number of images and labels in the training and test sets. A convolutional neural network is created by creating the necessary variables, inputs, and parameters. X-shape describes the shape of the input data. Two examples, 3 channels, 4 rows, 4 columns. W-shape describes the shape of the filter weights, 3 filters, 3 channels, 4 rows, 4 columns. With NumPy's linspace function, numbers are generated evenly spaced and assigned to X and W variables. Each filter has a B variable that represents the bias terms. In the conv_param variable, the stride and padding parameters are stored as a dictionary. A step is defined as how many pixels the filter moves at a time, and a padding is defined as how many rows and columns of zeros are added to the input data to allow more movement beyond the boundaries. This code does not show the conv_forward naive function, which convolutions the input data with weights, bias terms, and parameters. In the following code, the out variable holds the output of the function, and the underscore indicates the second output will not be used. This variable is used to test whether the function is correct by comparing the expected output to the actual output. Using rel error, you can calculate how close the outputs are by calculating their relative error between two arrays. A convolutional neural network is set up and tested using NumPy in this code. Using these variables and inputs, it uses the convolution operation and compares the output to a manually calculated value to ensure that the function is correct. Using Python code, this notebook performs the following steps. 1. It creates a new directory called CS231N in the current directory and its parent directories, if any, are missing. In reply to, it will change the current working directory to drive my dry drive folder name /CS21N. In addition, creates a new folder called CS231N from the Notebook Images folder, IV. The current working directory is changed to the root directory of the Google Colab instance /content/. Machine learning tasks commonly use Google Colab notebooks to organize images. In this code snippet, Python is used to perform simple convolutions. First, ImageIO and Pile libraries are imported, followed by the two images of a kitten and puppy. After resizing the images, the arrays are stored in array format. In the next step, two filters are applied, one to convert the image to grayscale and the other to detect horizontal edges. In the next step, we apply these filters to the input images using the conv_naive function and then store the results in the out variable. The imShowNoAX function is then defined, which displays images as uint8 and removes axis labels. A side-by-side comparison between the original images and the convolution results is then made using the PLT library. The following code snippet shows how to perform a simple convolution operation on images in Python and how to visualize the results. By using the alias np, it is first necessary to import the NumPy library. In order to produce consistent results, the pseudo-random number generator is seeded with 231. A normal distribution of random numbers is generated with the help of the np.randomRandN function. As a result, the first array, x, has 4 matrices that are 3x5x5. It has 2 matrices with dimensions of 3x3x3, meaning it is shaped as 2, 3, 3, 3. A two-dimensional vector with 2 elements, b, constitutes the third array. It has 4 matrices of dimensions 2x5x5 in the fourth array, doubt. We create a dictionary with stride of 1 and pad of 1 for conv_param. In the conv_naive function, the parameters x, w, b, and conv_param are used to perform convolution operations. The eval numerical gradient array function is then used to compute the gradient of the conv_naive function, considering each input array x, w, and b. There are 3 variables that represent gradients with respect to x, w, and b. dxnum represents gradient with respect to x, dwnum represents gradient with respect to w, and dbnum represents gradient with respect to b. As a result, the conv_naive function is called with the input arrays x, w, b, and conv_param, and the output is stored in the variables out and cache. This is followed by a call to conv_naive with doubt and cache, which contains the necessary data for a backward pass of convolution. Last but not least, the rel error function calculates the relative error between the analytic gradient computed by conv_naive and the numerical gradient computed by eval numerical gradient array. All input arrays dx, dw, and db should contain errors less than or equal to E8. A summary of the code is that each input array is tested for accuracy by comparing the analytic gradient with the numerical gradient, and the errors are then displayed. As a first step, the code creates an array shape of 2, 3, 4, 4 that stores the dimensions 2, 3, 4, 4 as part of a 4-dimensional array. 96 elements will be in this array. It creates a one-dimensional array with 96 elements, ranging from -0.3 to 0.4, using the NumPy function linspace. It has been set to be the product of the dimensions in X shape on the parameter num, which specifies the number of elements to be generated. The resulting array is then reshaped into a 4-dimensional array with the dimensions specified in X shape. There are 3 parameters in the following code: pool width, pool height, and stride. Maximize a pool forward using these parameters. As an input, maxPoolForwardNaive takes the array X and its dictionary pool param and performs a max pooling operation on X according to the parameters passed in. In this case, the original array X is ignored, while the result is stored in the variable out. Lastly, the code assigns the variable correctOut the correct output, array created in the previous step using the same parameters and input array. A comparison between the maxPoolForwardNaive output and the expected output is performed with this array. By using the rel error function that computes the relative error between 2 arrays, the last 2 lines of code print a message and the difference between the output and the correct output. This code creates an array, performs a max pooling operation on the array, and compares the output with what was expected. This function serves as a test for max pool forward naive. This code sets a random seed to ensure that the random number generator produces the same results every time. A standard normal distribution is used to create a four-dimensional array of shape 3, 2, 8, 8. Third line creates another four-dimensional array with values drawn from a standard normal distribution. Fourth line creates a dictionary with three key value pairs, specifying the pooling filter 2x2 height and width and stride. Fifth line calculates the gradient of the first element of the output of max pool forward naive function with respect to the input x using a val numerical gradient array. Input values are varied small to approximate the gradient numerically. Next, we call the max pool forward naive function, passing x and the pool param dictionary as inputs. Based on the parameters specified in pool param, this function performs max pooling on the input array x and returns an output array out, as well as a cache object containing information about the backward pass. As part of the last line, the max pool backward naive function is used to calculate the gradient of the output DOUT with respect to the input x. For the final check, the difference between the numerically approximated gradients dx num and the calculated gradients dx is printed. It is expected that the error would be very small on the order of E12, indicating that the backward pass was properly implemented. Steps for installation and setup are outlined in the provided Python code. Through the use of the sent-cd command, the code changes the current path to drive my drive, folder name, CS231N. There are a number of files and scripts required to install up the CS231N course in this folder. A script or file name, in this case setup.py, is followed by Python. Within Google Collaboratory, you can execute Python scripts and files. For the CS231N course, setup.py is responsible for building and installing the needed dependencies and libraries. BuildX builds and installs the C extensions for the libraries. Instead of the default location, the built files are generated in the current directory. A Python script is used to build and install dependencies, and where the built files should be generated are specified in this code. Both a naive and a fast implementation of a convolutional layer in a neural network are tested in this code. Several lines in the first section import libraries, set a random seed, and set input, weights, bias, and output variables. Following that, the code calls the convolutional function for both the naive and fast versions and calculates the running time for each. In the next step, the results are printed and the speedup factor is calculated. Also included in the code is a function called rel error that calculates the relative error between two matrices in order to display the difference between the two versions. Additionally, we compare the speed and accuracy of both the naive and fast implementations for the backward pass of the convolutional layer. A fast implementation of a convolutional layer in a neural network is demonstrated in this code for performance and accuracy improvements. In this code, we are testing the speed and accuracy of a fast implementation of a max pooling layer in a convolutional neural network. As a first step, modules and libraries from the CS231N.FastLayers library are imported, such as max pool forward fast and max pool backward fast. Then, an array of data X is generated along with its derivative DOUT. Arrays from these arrays are used in max pool forward and max pool backward. Among the pooling layer's parameters are the height and width of the pool and the stride. Both the naive and fast implementations use these parameters. By using the time function, the code times both the fast and naive max pooling implementations. A table of the results is printed along with the time taken to implement each implementation, as well as the speedup achieved by the fast implementation. Using real error, the code compares the output of naive and fast implementations to determine the relative error. Accordingly, the fast implementation should be close to 0.0, indicating that the naive implementation has not significantly changed. In the backpropagation step, the code also times the execution and compares the output of the naive and fast implementations. Using this code, convolutional neural networks can be tested and evaluated for their speed and accuracy using a fast pooling layer. In this program, gradients are checked numerically for the functions conv_ReLU_pool forward and conv_ReLU_pool backward. We start by importing the NumPy library and setting a seed so that results are consistent. Next, random arrays are created for the input data x, weights w, biases b, and output gradients dout. The convolution and pooling parameters are stored in dictionaries called conv_param and pool_param. After that, we apply the conv_relu_pool_forward function to the input data, weights, and biases using the convolution and pooling parameters we provided. Firstly, convolution is applied, then relu activation is applied, and then maximum pooling is applied. Variable out, which contains the output, and variable cache, which contains the intermediate values, are stored in this function. Following the calculation of the gradients on the output gradients and the cached values, the conv_relu_pool_backward function is applied to the output gradients and the cached values. In this case, gradients dx, dw, and db are stored in different variables. By using the eval numerical gradient array function, numerical gradients can be checked. Using the provided step size, this function computes the numerical gradient for a given function and its inputs. After the numerical gradients are computed, the value of the relative error is calculated by comparing the results with the analytical gradients computed in the previous step. Gradients must be calculated accurately if there is a small relative error. By using numerical gradient checkers, this code tests the accuracy of conv_relu_pool_forward and conv_relu_pool_backward functions. The function ensures that gradients are accurately calculated and can be used to create a larger neural network. In this code, we calculate the gradient of a convolutional layer using the two functions conv_relu_forward and conv_relu_backward from the layer utils module of CS231N. Firstly, the code initializes a four-dimensional input array X and a four-dimensional weight array W for the convolutional layer with a random seed to ensure reproducibility. Two feature maps are in the input array, each measuring 3 to 8 by 8, and three filters are in the weight array, each measuring 3 by 3 by 3 by 3. Afterwards, we initialize a bias vector B and a derivative of the output dout. Additionally, stride and pad of the convolution are set. Next, conv_relu_forward is used to calculate and store the output of the convolutional layer. Conv_relu_backward uses the cache variable to store gradient information for computation. After that, conv_relu_backward is called to calculate gradients of convolutions based on inputs, weights, and biases for the convolutional layer. This is done using the function eval numerical gradients array, which approximates gradients based on small input differences using the analytical gradients dxnum, dwcornum, dbnum. An error between the analytical and numerical gradients under E8 indicates that the gradients are correct. In other cases, the error statement is printed as well as the numerical values. A convolutional layer gradient is computed and validated via analytical and numerical techniques in this code. It creates a variable model for the three-layer convnet model and assigns it to that variable. It then generates a random array X of shape 50, 3, 32, 32, using the NumPy library by setting the number of data points to 50. Also, it generates a random array of size 50 with 0 to 10 values. The code then passes in X and Y random arrays to the loss function of the model. The loss and gradients are calculated based on the inputs and returned. Without regularizing the loss value, the code prints its initial value. This is followed by setting the regularization parameter in the model to 0.5 and calling the loss function again. After the new loss value is printed, the old value is removed. The purpose of this code is to create a model and enter data into it to calculate an initial loss value. Once the model has been updated, it calculates the loss value again to show the effects of regularization on the result. The purpose of this code is to define a neural network model and evaluate its performance. Input points are set to 2, and input dimensions are specified as a tuple of 3, 16, and 16. 0.0 is also set as the regularization term, and 10 is the number of classification classes. For reproducibility, two arrays are created with NumPy, X with dimensions 2, 3, 16, 16, and Y with dimensions 2, representing input data and its corresponding labels. After that, we construct a three-layer convnet model using a given number of filters, filter size, input dimensions, and hidden dimensions. Losses and gradients are calculated as a function of the model parameters. It is then calculated and printed for each parameter in the model the relative error between the numerical gradient and the model's gradient. It is desirable to have small errors, but it is noted that relative errors up to E2 can still signify a correct implementation. For each parameter, we print the maximum relative error. In this case, in this code, the seed for the random number generator is set to 231 in the first line, np.random.seed231. Reproducible results are ensured by generating the same random numbers every time this code is executed. The second is, a number of 100 data points will be used for training in the following line, numTrain equals 100. The third point, using the small data dictionary, a small dataset is created. In training, data points are limited to the first 100, while validation data remains constant. The fourth point, in the line model, equals 3-layer convnet weight scale 1e-2, an instance of a convolutional neural network model with a weight scale of 1e-2 is created. The fifth point, initiating the solver. The solver is initially initialized using the model, the small dataset, and other parameters such as the number of epochs, batch size, and update rule. In addition, the lineSolver.train command trains the model using the parameters and dataset you specify. During this step, the model parameters are updated using the specified optimization technique, in this case, ATOM, and the model performance is evaluated using validation data. By using ATOM optimization, a small dataset is used to train a small-scale convolutional neural network model. Using this code, you can experiment with different modeling and optimization techniques on a smaller dataset before applying them to a larger one. It runs the check accuracy method from the solver class first, and then passes the small data dictionaries xtrain and ytrain data as input. In this method, the model's accuracy is calculated based on the training data and returned as a value. Small data, along with a string representing the type of data used, are then printed. A machine learning model's final validation accuracy is printed using this Python code. On a small dataset, it evaluates the accuracy of the model by using check accuracy from a solver class. Two parts of this dataset are presented, input data, xval, and label data, yval. Predictions are made with the trained model using input data and labels. A percentage of correctly classified data points is calculated when this model is validated by comparing predictions with actual labels. Printing the validation accuracy and labeling it helps the user to know what it refers to, in this case, small data validation accuracy. Basically, this code prints the accuracy of a trained machine learning model on a small dataset. Python code created this figure containing two subplots arranged vertically, 2 rows and 1 column, using matplotlib. The first subplot, plt.subplot211, plots the values from the solver.loss history list with O stands for circular points, X representing iteration numbers, and Y representing losses. To label axes, use plx label and pl.y label. Plotting the values from solver.train ac or history and solver.val ac history with circles as lines is the second subplot, plot 212. This function adds a legend to the plot with the labels train and val and a location of upper left. As indicated by the x-axis, the epoch number is represented by the x-axis and the accuracy is represented by the y-axis. A figure is displayed using the peltot.show function at the end of the code. The code is usually used to visualize the progress of a neural network during training, with the loss decreasing and the accuracy improving. By specifying a weight scale, hidden dimension, and regularization parameter, this code creates a 3-layer convnet model. As a result, it creates a solver object containing the model, dataset, and other training parameters such as number of epochs, batch size, and change rule. Using ATOM as the update rule with a 1e3 learning rate, we selected the rule for updating. The code trains the solver object, which in turn trains the model on the given dataset for the specified number of epochs, printing out the loss and other information every 20 iterations. By using the ATOM update rule, the 3-layer convnet model is taught on the dataset for the given number of epochs, and the loss is minimized. The Python code prints the final training accuracy for a given dataset. Using inputs of the training data and training labels, the function checkAccuracy is called from the solver object. A value is returned by the checkAccuracy function once the model has been evaluated on the given data. After printing this value, it is accompanied by a descriptive label. A code can be used to evaluate a model's performance on a specific dataset and determine whether it needs to be adjusted or retrained. It checks the accuracy of a model on a validation dataset with this Python code. In order to calculate accuracy, it uses a method called checkAccuracy from the solver class. It prints the text full data validation accuracy, and in the second line, it calls the checkAccuracy method with two variables, dataXval and dataYval, representing input features and corresponding labels. This calculation then produces the final validation accuracy of the model based on the validation data that is provided. Importing Visualize Grid from the CS231N library is done in this code. An array called W1 is used to store the weights of the model's first layer. The array is then transposed to have the first and fourth dimensions switched and passed to Visualize Grid. Matplotlib's plt.imshow function transforms the weights into a grid and displays them as an image. There will be the same number of rows and columns as W1's first dimension, with each cell containing an image of its weight. As a final step, Matplotlib axis and GCF functions are used to set the size of the grid and remove the axes before using plt.show to render the image. This code visualizes the weights of the first layer of a neural network. So that the random number generator produces consistent results, the first line of code sets a seed. Following this line are the variables n, c, h, and w. Input data will be in this shape. Using the numpy random.randn function, the x variable is set up to be used as a 4D array of random numbers. A mean of 10 and a standard deviation of 4 are then calculated from these numbers. In the following lines, you will see the shape, mean, and standard deviation of the incoming data. Ideally, these values should be close to 0 and 1. A call is then made to spatial batch norm forward, which takes in the data, gamma, and beta values, and some batch norm parameters. The spatial batch normalization function reduces the effects of covariate shift on neural networks by performing spatial batch normalization on the input data. After that, the outputs from the function are printed, which should have shapes of 2, 3, 4, 5, and mean and standard deviation values that are close to the given gamma and beta values. Lastly, gamma and beta values are changed in the function. It is recommended that the means and standard deviations of the output be closer to the new values rather than the means and standard deviations of the inputs. In this example, the batch normalization process is able to normalize data using any given gamma and beta value. The purpose of this code is to test the performance of spatial batch normalization on test data. The procedure begins with setting a random seed in order to maintain consistency in the results. N, C, H, and W are initialized to represent the batch size, total number of channels, height, and width of the input data. The next step is to create BN param as a dictionary with the key mode set to train. Gamma and beta parameters are then initialized with np.1s and np.0. With np.random.randn, the for loop prints out a random input value x for 50 iterations. A spatial batch norm is then applied to the input data, along with the parameters gamma, beta, and bn param. The output data is normalized based on the mean and variance calculated in this function. In order to indicate that we are now in the testing phase, bn param mode is set to test. X is then passed through spatial batch norm forward again as random input data. Instead of using the same parameters as in the past, this time the function will perform the normalization on the input data as part of the test procedure. As a result of normalizing the cache values, the a-norm and score variables are set. After normalizing the data, we print the means and standard deviations to see how they compare with our desired means and variances. This code is intended to compare the performance of spatial batch normalization during training and testing to make sure it is working correctly. A random seed is set in the first line of the code to ensure the generated random numbers are consistent between runs. There are 4 variables defined here, n, c, h, and w. These variables correspond to the number of data points, the number of channels, and the size of each data point. By using the NumPy library, the third line creates a 4-dimensional array x. Random numbers are generated using a normal distribution with a mean of 12 and a standard deviation of 5. Next, 2 one-dimensional arrays, gamma and beta, are created, also containing random numbers. Following this line, we create a 4-dimensional array called doubt. which contains normal distribution random numbers. Neural networks use this array to represent their output from previous layers. Next, we create a dictionary named bn-param, which has one key-value pair, mode train. A batch normalization function uses this value as input. In the following 3 lines, lambda expressions are used to define 3 functions, fx, fg, and fb. The functions use the spatial batch norm forward function with the arrays x, gamma, beta, and the dictionary bn_param. With respect to the inputs x, gamma, and beta, the gradient of the batch normalization function is calculated by using the eval numerical gradient array function. On line 4, the spatial batch norm forward function is called with the same inputs as those used in previous lines. Cache object and output are returned. Next, the output of the previous line and the cache object are passed to the spatial batch norm backward function. Based on x, gamma, and beta inputs, this function calculates the gradients of the loss function. In the last 3 lines, errors are calculated between the numerical gradients and the analytical gradients for the inputs x, gamma, and beta. It is possible to compute the relative error between 2 values by using the rel error function. It creates random input data, runs the batch normalization function, and computes the gradients of the file output. Tests and validations can be performed on a neural network's implementation of a batch normalization function can be conducted using this tool. By checking the means and variances of features after and before performing spatial batch normalization, this code checks the training time forward pass. In order to ensure reproducibility, the seed has been set to 231. Afterward, n, c, h, and w have values of 2, 6, 4, and 5 respectively. An image size of 4 by 5 and 6 channels make up this 2-dimensional dataset. Using the np.random.randn function, we create a 4-dimensional array x that generates random values with a mean of 0 and standard deviation of 1. As seen in this example, x has the form nchw, which in this case is 2, 6, 4, 5. In this example, we added 10 to each of the np.random.randn, n, c, h, and w values, resulting in a mean of 10 and a standard deviation of 4. Using this dataset, we can simulate a more realistic situation. X is then reshaped as n-ta-g-1, where g is assigned a value of 2. The resulting shape of xg is n-c-w, which in this case is 4240. As a result, you would expect each row of xg to have a mean, standard deviation close to 0 and 1, respectively, indicating that the normalization was done correctly. After gamma and beta have been initialized, gamma and beta parameters for spatial group normalization are defined. A scaling parameter is gamma and a shifting parameter is beta, and both have the shape 1, c, 1, 1 to match the input dimensions. A training mode is additionally specified in the bn-param dictionary. Following that, spatial group norm forward is called with inputs x, gamma, beta, g, and bn-param. Backpropagation is performed on the normalized output and the intermediate cache returned by this function. For each row, the means and standard deviations are printed again to ensure that the normalization was truly achieved. This code generates a random dataset, performs spatial batch normalization on it, and compares the original data to the normalized output to verify that normalization worked. To compute the gradient of a spatial group normalization function, use this code. The function outputs an array representing normalized values based on input parameters gamma, beta, g, and gn-param. Whenever the code is executed, a random seed is set to ensure that the same random numbers are used. Following this, values are assigned to the variables n, c, h, and w. Array x is created by multiplying 5 by a random array of size 2, 6, 4, 5 with a constant value of 12. A random value is assigned to each array. Gamma and beta are the 2 arrays that are created. The value of a variable, doubt, is assigned at random. Additionally, the code defines 3 functions fx, fg, and fb, which compute normalized outputs using spatial group norm forward. All the functions require the same parameters, but they use different inputs. A numerical gradient is then calculated using the function eval numerical gradient array. To check the accuracy of the gradients, this is done. With the real error function, we compare the gradients of gamma, beta, and x calculated with those computed with spatial group norm backward. A good gradient accuracy is between 1E12 and 1E07 errors, which indicates good accuracy.